Let us begin lecture 20. So, in next couple of lectures, we will be discussing pourbaix diagram. We have already started looking at pourbaix diagram because it is an important aspect, an important feature in electrochemistry, and when you look at the corrosion, then this understanding of pourbaix diagram is very, very essential. Now, as we have told that the pourbaix diagram is nothing but a stability plot between of different phases between in the plot of E versus pH. This is the pourbaix diagram. This is basically stability diagram. Now, whenever we talk about pourbaix diagram, we must understand certain facts. And what are those facts? One, we would only consider reactions involving oxygen, H2O, H plus, OH minus, metal ion, metal ion, metal hydroxide or metal oxide. So, here we are talking about only this kind, there could be several complex oxides involving these many species. And remember, we will not consider any other species. Second part, we would consider reactions, and those reactions can be categorized into 4 major reaction stages. One reaction of course, we will not consider, but that indirectly affects the pH of the system, but that will not be plotted in the pourbaix diagram. And certain reaction only involve metal and metal ion, certain reaction would involve hydrogen ion, H2O, that means water, metal ion, or and hydroxide, metal hydroxide or metal oxide. And certain reactions would involve metal, H2O, hydrogen ion and metal hydroxide or metal oxide. But between these last two cases, one case we would see that there is no electrons involved for this particular reaction, but other case we have electrons involvement of electron. So, let us categorize those reaction. Let us categorize those reactions. One reaction, for example, in water we sometime we have dissolved of carbon dioxide that can react with H2 and form H2CO3. So, as I have told that this reaction cannot be plotted in pourbaix diagram of a metal, but actually whenever we have this is an acid, this acid would have, this is a weak acid, but still it would lead to certain pH of the system that can affect the corrosion stage, and this is a typical acid that affects the corrosion of rebar, that means reinforced bar in which is basically embedded in concrete mixture. But this particular reaction, if you see, it does not involve any metal, no involvement of metal. So, this is kind of type 1, I can say this is type 1 reaction. Now, type 2 reaction, for example, metal, I can have N plus Ne equal to M, M is the metal, and now since I do not know what is the oxidation number, then N plus, for example, if it is a copper plus going to copper, N becomes 2, Fe plus 3 going to Fe, N becomes 3, like that way we can have the value of N. So, N is basically nothing but the oxidation number. So, this is this particular reaction, if you see carefully, it depends on potential. Why? Because this reaction can be expressed with in terms of Nernst equation. But this particular reaction does not involve any H plus ion. So, this H plus ion is not involved. So, then the pH of this particular for this particular reaction would have no effect. So, we can say that this is function of potential, but it is not a function of hydrogen ion concentration. So, this is a function of E, but not a function of hydrogen ion. So, or not a function of pH. So, whenever we have hydrogen ion presence, we can express in terms of pH. This we call it type 2. We can have another reaction. For example, let us say I can have M, which can react with 2H2O. It can go to M OH whole 2 plus 2H plus 2E, and that time N is basically 2. This is another reaction we can consider that can happen in water when a metal is exposed to moisture or water, aqueous medium. So, now here we see that it is a we have here also we can express this particular reaction in terms of Nernst equation RT2F, since number of electrons involved for this reduction process is 2F 2 ln activity of oxidant. Now, here the oxidant part is this part and reductant part is this part. So, I can write this particular reaction in reverse. So, MOH whole 2 plus 2H plus 2E equal to M plus 2H2O. So, now here the M has got 2 plus. So, the 2 plus going to 0. So, it is a reduction. So, this reduction process we can express in terms of A M OH whole 2 A H plus to the power 2 A M A H2O. This A is nothing but the activity. I can express this in this form. Now, interestingly, this particular equation, once we express in terms of Nernst equation, it becomes a function of potential. But here if we consider this particular hydroxide to deposit back to or to settle down, that means because of its very low solubility product, solubility constant. So, this particular thing, if it is we consider to be pure and solid, so I can consider activity to be 1, and if we consider it is a pure water, we becomes activity 1. Metal, of course, it is pure and activity 1. So, then this equation we can write in terms of E0 plus RT 2F ln activity of H plus, we can write so we can express this reaction through this Nernst equation. So, you see that it is function of potential, at the same time it is a function of H plus ion presence or function of pH. So, this reaction becomes the type 3 category. Now, we have one more reaction that is also possible, where let us say this is 1, this is 2, this is 3. Now, we have one more, which is M 2 plus 2 H2O. It can go to MOH whole 2 plus 2 H plus. So, this reaction we can also have, where you see that it does not involve any electron. So, if there is no involvement of electron, so we cannot express the equilibrium for this particular reaction in terms of potential. We cannot express. But this is a chemical reaction. So, these chemical reactions can be expressed in terms of equilibrium constant, which is nothing but activity of product. So, activity is MOH whole 2 H plus square, activity of M2 plus and activity of H2O square. So, if we see this reaction, is this reaction. So, if we consider the forward reaction, so I can express K to be like this, whether forward or backward it does not matter, because it is equilibrium constant. So, I can write this. Now, once we write this, then we can also simplify this equation. This equation can be written log K equal to, as we have mentioned, MOH settle down. So, it is a solid and that too pure. So, MOH whole 2 we can consider 1, H2O still we can consider 1, because it is a pure water. Then it goes to, the equation boils to log activity of H plus activity of M2 plus this. So, I can write, if I convert activity into concentration, assuming that it is maintaining ideal solution. So, in case of ideal solution, activity becomes concentration. So, that case I can write log two minus log two plus. Now, we see that in this final equation becomes, I can put it as pH, because this is nothing but minus of pH with a 2 sign, because 2 would come here, minus log of M plus 2 plus concentration. So, this is an equation which can decide the stability of M2 plus and stability of MOH whole 2. But this particular reaction does not contain potential. So, the potential cannot decide this particular reaction, potential cannot tell me the stability of this particular reaction, because it does not involve any electron acceptance or electron, if the system is not also giving away electrons. So, no cathodic or no anodic reactions are taking place in this entire reaction. So, it is pH dependent function of pH, because here we have pH, but it is not a function of potential. So, this is type 4. So, this equation becomes type 4. So, the type 4 equation can be expressed with this. Now, whenever we are having these equations, for example, equations like this, equation like this, and finally, we are boiling it to we are getting to this particular equations or equations like this. These equations would enable us to plot pourbaix diagram and also enable us to find out the stability of M2 plus M or M hydroxide, because here we are only considering hydroxide. We can also have set of reactions involving oxides also, metal oxides. Now, as I have told you that first one was this many species are considered depending on the possibility of formation of this species or this species, and or the possibility of having dissolved oxygen or deaerated. And then second part was we can have 4 types of reactions, but mainly we are considering type 3 to type 4. So, these reactions we are considering to happen in the aqueous system, and that would lead to the plotting of E versus pH, and that would give us the pourbaix diagram. Now, interestingly, the pourbaix diagram will not be complete if we do not consider 4 reactions involving only oxygen, dissolved oxygen of course, hydrogen, hydrogen ion, and 2 other species which are OH minus and H2O. So, now we can have 4 more reactions involving H plus, OH minus, O2, H2O, H2. So, this 5 species can have following reactions: 1 H plus 2E equal to H2 to O2 plus 4H plus 4E equal to 2H2O, 3 O2 plus 2H2O plus 4E equal to 4 OH minus, and 4th H2O plus 2E equal to H2 plus 2OH minus. Now, you see all 4 reactions we have already discussed before. These 2 reactions are possible in pH less than 7, that means acidic medium, and these 2 reactions are possible when pH is greater than equal to 7, neutral or basic medium. Now, all 4 reactions you see that the electrons are involved, and all 4 reactions we have H plus ion presence in these 2 cases and OH minus ion presence. Now, whether we have H plus or OH minus, we can express Nernst equation in terms of potential as well as pH. So, now all 4 reactions are function of potential and function of pH. So, in these 2 cases it is a function of pOH, which can be written in the form of pH. Now, this calculations we have done it before. You just go back and then see some of the earlier lectures, you will see that all 4 reactions we have tried to find out the reduction potential as a function of standard reduction potential and the pH of the solution. And also we have tried to plot those reactions as a function of pH. If you go back, you can have a look at it again. So, but these 4 reactions also are function of potential and function of pH. So, that means logically we have 2 types of reactions, one which involves 3 types, one which involve potential. So, that means 3 type 1 only potential dependent, but pH independent. Second type potential dependent and pH dependent, and third type potential independent and pH dependent. So, these three would allow us to find out a pourbaix diagram. Now, in addition to that, we can have the third criteria condition. So, this pourbaix diagram are basically a thermodynamic stability diagram. It does not involve any kinetics. Now, from this diagram we will not be able to tell at what rate, if there is any corrosion of a metal in the aqueous medium, what rate it is going, we cannot be able to tell from this pourbaix diagram, because it is a thermodynamic stability diagram. Why? In order to find the pourbaix diagram, we have to find out those equations, the equations like what we have shown. So, this equation like this one or this one or this one, and then finally of course this equation and the equations related to all four reactions involving hydrogen ion, oxygen, water, hydroxide and hydrogen. We have to get the information about standard chemical potential. And whenever we talk about standard chemical potential of a species, that indicates that they are in their activity 1, and whenever we are talking about activity 1, we assume that they are pure state. So, since we have understood that what are the species that are possible in combination, of course, we have chemical potential of metal, chemical potential of metal ion, chemical potential of oxygen, chemical potential of hydrogen, chemical potential of metal hydroxide, chemical potential of metal oxide, H2O, OH minus. Are we missing anything? So, metal, metal ion, oxygen, hydrogen plus, metal hydroxide, metal oxide, H2O, OH minus, and of course, H2. We have to make use of the standard chemical potentials of all the species in a particular reactions, particular set of reactions. We have to consider those chemical potentials. Now, how do we get it? For example, K, if I consider the activity, this equilibrium constant is nothing but delta Z0 with a negative sign here. Now, delta Z0 we can write as we have done it before, the summation of chemical potential of standard chemical potential of product minus summation of chemical potential of reactant. So, this will give us free energy change. From that we can calculate activity, this equilibrium constant. And similarly, we have another reaction NF E0 equal to delta Z0, which is similar like this. We can have product minus summation of product of this chemical potential, standard chemical potential of all the species that are involved in a reaction, and the summation of standard chemical potential of reactants in that particular reactions. For example, M2 plus Ne equal to M. Here we have this chemical species, this species, and of course, here we are considering 2, that means instead of N we can put 2E. So, here this is we have to consider chemical potential of 2 plus, we have to consider chemical potential of M, and of course, we can consider the chemical potential of electron also. That chemical potential will be used up in 2F. So, we have a relation for this. We are not getting a detail of that relation, but this one contributes to this 2F. Delta Z0 comes from chemical potential of M minus chemical potential of M 2 plus. So, this is delta Z0 minus 2F E0. So, this 2F is related to this 2 electron, and of course, that is also related to chemical potential of electron. As we have said that we are not going detail derivation of this particular relation from the chemical potential of all the species involving electron also, but for our understanding we can see that this electron is contributing this part, and this one is can be found out from this relation, and this comes from this. So, we see that these are all thermodynamic data. These are all thermodynamic data, and these thermodynamic data will be used up to find out reaction equilibrium constant or the chemical potential or the standard reduction potential, and this equilibrium constant will be used for type 4 type of this particular reactions, and in this case K equal to delta Z0 minus RT, and in this case E0 equal to delta Z0 NF minus. So, there we have application of delta Z0 or the application of standard chemical potential of the species. In addition to that, so we have to calculate this K or E0 from standard chemical potential data, but sometimes we do experience ion activity to be not to be 1. So, that case we have to make use of Nernst equation, where we also have contribution from the ions of metals. So, then finally, we would construct pourbaix diagram. So, these are the basic consideration on which this diagram will be built on. So, in our next lecture, we will try to find out one example in the nickel system, nickel H2O system. We will try to see the pourbaix diagram, and we will start from the chemical potential of different species, and we will end up getting that diagram, and then we will see that yes, in this position if I am, then I will get metal remaining as metal. In this position if I go, I will get metal ion formation or corrosion, or at certain region we might get metal hydroxide which will settle down. So, we consider it to be a passivating zone. So, let us stop here. We will continue our discussion in our next lecture, where we will start with the pourbaix diagram calculation in case of nickel H2O system. Thank you.